Bismillah ar-Rahman ar-Rahim. Welcome back to speech processing. And now we are ready to begin our journey of digital signal processing, and more specifically of the signal processing uh, pertaining to speech signals. So that's our next topic. It's going to continue for I think at least for 5 to 6 lecture videos. And we'll be looking at various types of signal processing that are relevant to what we want to eventually do. So our course now would be that we will cover signal processing, and then this will ultimately culminate at the level of one representation of signals in terms of features on which we need to eventually perform machine learning. And the second goal would be that we will be developing several speech processing techniques just within the domain of signal processing, and we'll be doing interesting speech processing tasks using them. So the idea is that many speech processing tasks can be done with decent performance and accuracy just by using these signal processing techniques. We don't even need machine learning for them. So we'll be doing a lot of interesting stuff here. So our journey will begin with time domain methods, and I'll be giving you more details about what these are in the following slides. All right, just before I begin, these slides were co-developed by myself and my advisor, mentor, teacher, Dr. Sarmad Hussain, who advised me during my master's thesis, which was on speech processing, who taught me speech processing at FAST. So I worked with him for several years, and these slides were co-developed by both of us. So both of us use them. Obviously, his versions have now evolved beyond the point where we basically took our separate routes of teaching, and mine have also developed, but at least the core of these slides, and I think the template and the design also remain the same. So just a disclaimer and also an acknowledgement of all of his contributions to both whatever I know about the subject and also the contents that I'll be covering from here onwards. The main book that we'll be following from this lecture onwards would be The Digital Processing of Speech Signals. I am sure that your version may not look like this one. This is one particular version of it, but this is Digital Processing of Speech Signals by Rabiner and Sheffer. I think it is also available online for download, so you can just use a soft copy, but make sure that you read the book as well. In places, so this is not a very easy to read book. This is not like the speech and language processing by Jurafsky and Martin. This is a more a rather more involved book. If you're from the engineering background, some of the concepts would be initially simpler for you, but our aims may make the ground more plain for everyone, because our aims are not to, or at least not just to learn the formulas or to be able to do maths with that. We also want a complete understanding, a deep and thorough understanding of what those formulas represent, because our tasks will go beyond just the representations and just the mathematical modeling of these various acoustic phenomena. So yeah, keep the book handy, start reading the book, and let's begin. All right, so our goal with this lecture series around digital signal processing would be divided into 3 parts. Today we'll begin with some of the fundamentals of digital signal processing. Hopefully we should be able to cover most of it in this lecture. And then we will start with time domain speech processing methods, and this would include many interesting and exciting methods, and at places I'm sure you'll be surprised that some of the things that we consider to be quite complicated and which in our heads we believe that those things would require a lot of machine learning can simply be done just by using fixed thresholds and rule-based systems and just plain old speech processing techniques using signal processing. And then we'll move on to frequency domain speech processing methods. And when we end that, at that point, we would also have a list of features that we're going to use throughout the machine learning part of the course. So hopefully around lecture 20, around that time, we should be able to be like done with this, and we'll be done with all of this, and then we'll be starting with our machine learning journey from that point onwards. All right, so first things first. What is signal and what is speech? I think that we have already in a previous lecture completely covered the domain of what sound is and what signals are and what speech is and what noise is and so on and so forth. So here just going over some of that. So speech can be represented in terms of its either the physical signal, that is the acoustic waveform, or it could be represented in terms of the message content or information. So this is more like the second one. The message content or information is more like the abstract level things. So for example, if we're talking about phones, we're talking more about the acoustic waveform, the acoustic phenomena. If we're talking about fundamental frequency and first formant and second formant, we are again talking about objective, observable, measurable, quantitative phenomena. Whereas if we are talking about perception of those phenomena or interpretation of those phenomena in language, so for example, when we talk about phonemes, or we talk about syllables, or we talk about pitch, or we talk about all of these stress and so on and so forth, those things are no longer clear and objective and measurable always. Some of them are subjective, some of them are just based on the perception. So several filters are basically being applied to the original objective signal, the measurable signal, to come up with the qualitative, the more subjective interpretation or the impression of that signal. So that's what we mean here. So for example, when I'm speaking, you can obviously measure the amplitude and the frequency and the F1 and F2 and F3, the formants or the fundamental frequency. You can measure those things, but what I'm saying also has a meaning to it. It also has a pragmatic meaning to it. It also has semantics and a syntax to it. So all of that is the message content or the information. So both of these things could be used to represent speech. When we talk about the physical signal representation, which is what we'll be interested in the next few lectures, now we can represent signals as a time domain waveform. So here you can see the waveform of a vowel schwa. You can see it's periodic. You know why it's periodic. You know how it's related to the phonation happening at the vocal folds, and you also see the spectrogram of the same vowel. And by now you're experts of reading these spectrograms. You maybe for schwa you also know the kind of frequencies that you'll be hitting given a particular length of a vocal tract and so on and so forth. So think of this as more like the recipe of constructing this signal. So the speech, the frequency domain representation is more like the recipe of how to reconstruct this signal. Or you could think of it also as a breakdown of the signal in terms of its the different frequencies that are present in it. So as part of these lectures, we'll be covering a principle that is actually the core of all of signal processing. And that principle we'll cover in a lot of detail, and we'll be going into its mathematical background as well as its intuitive understanding and also a thorough understanding of the principle itself. And that principle would lead us to studying things like the Fourier series and the Fourier transforms. The idea there is that we can represent any periodic signal as a weighted sum of sinusoids. So we can use a weighted sum of sinusoids. We can use the harmonic series there. We can use the fundamentals and the harmonics. So we can add those sinusoids up, and then we can basically construct or represent. So it's basically like saying the same thing from two different directions. We can construct any periodic signal using those sum of sinusoids, weighted sum of sinusoids, or we could basically deconstruct or analyze any signal into that form. So that would be a very groundbreaking and a very central concept. Groundbreaking for us because this is the first time we'll be studying it, but in terms of its interpretations in signal processing, it has a very core and a very central significance in the signal processing methodology. But we'll get to it once we reach the frequency domain methods. All right, so when we're talking about, so let's begin with the representation of speech signals. So once we get speech from, let's say, a microphone, we need to somehow represent it in our systems. We need to store the speech in the form of, say, a file or a recording on a cassette or a recording on a CD or whatever. We need to represent it somehow. So for the representation of speech signals, as in the representation of any other real world phenomena, we come up against these two competing requirements. So the first requirement is that we want to preserve the message content as much as possible. So we want to basically preserve it in as real, as natural way as possible. However, there is a competing requirement that if we want to preserve the message content completely, usually the size of the representation grows. So if you're storing a file on your computer, if you want to store it in a very high quality that would preserve the message content, that would preserve more than what we actually need for most of the tasks. However, the file sizes would be huge, which means that it would be difficult to store it and difficult to transmit it. So the competing requirement is that we want to lower the size to efficiently and conveniently store and transmit the files. But when we make the size smaller, the preservation of the message content could suffer as a result. So therefore, what we're going to see here is, as you also see in the domain of image processing and representation of basically videos and so on, that there are certain losses which are acceptable for various requirements. So if you require speech for, let's say, telephonic conversations, one type of a bandwidth, one type of a frequency representation might be enough, and the file sizes might be smaller. If you want a more high quality audio recording for, say, music or recitation or whatever, if you want something to preserve frequencies beyond just the human speaking common frequencies that we use for communication, then we can use bigger file sizes and so on and so forth. So we're going to get into that, but these are two competing requirements. These are trade-offs that we need to carefully decide about before we decide on the file format, so whether it's going to be MP4 or MP3 in case of audio, or it's going to be WAV, or it's going to be whatever the file type that we want to use. So we're going to be looking at some of that. All right, so the goal of digital signal processing, just at a very high level at this point in our course, the goals are basically these three. So representation of speech signals in digital form. So we're going to begin by learning about that. That's our immediate first topic. That's what we're going to cover in this lecture, inshallah. Then we need to come up with ways of processing digitized speech as per application needs. So for example, you want to detect all the vowels in a recording, or you want to separate out between human speech versus silence, or speech versus noise, or speech versus music, or you want to separate between vowels and, say, consonants. So all of that are application needs, and we would be coming up with digital signal processing methodologies to basically be able to do those tasks. And then finally, we will be coming up with techniques for analyzing signals and for synthesizing signals. So what do I mean by that? So given a recording, I want a way of breaking down that recording into its components and somehow storing it. And given components, I want to come up with a way of combining them and reconstructing a signal. So synthesizing a signal would mean constructing a signal. So constructing a signal from scratch, let's say. And analyzing a signal means, given a signal, I want to break it down in interesting ways into its components, and maybe at that time, maybe even tweak the components, modify the components, and then reconstruct it into a new form. So this would include noise removal, echo cancellation. So we won't be covering those. We won't have time to go into those signal processing tasks, although those are extremely interesting and very useful. But how do you denoise a particular recording? How do you remove echo, which is not a very straightforward task? How do you do all of those interesting things? So the tools that you're going to be using do enable you to do most of those things, even adaptive filtration, which of your audio files. However, we won't be able to cover all of that in detail. It's one semester, so that's all we can cover in one semester. One of these days, I really need to start thinking about maybe breaking this course into two parts, where one part is just purely acoustics and linguistics, and another part which is purely machine learning. But yeah, that day will come when we have enough interest from students, and we have enough body of students who are interested in taking speech into like a beginner course and an advanced course. But that time is not now, so we won't be covering those things in this course, but that comes under the same umbrella. Like breaking down signal into its component, remove the components that you don't need, for example noise, and then reconstruct the signal, which is now a clean signal. So all of those things are part of digital signal processing. All right, let's begin with the first task of representation of speech signals in digital form. So the first thing that we will be discussing now is not just limited to speech or audio. It's basically a broad differentiation between the real world and the digital world. And this is something you come across always in every domain wherever your interfaces are dealing with the real world. So the difference is that the real world is continuous. The real world is made up of real numbers. And I'll explain what I mean by that. Whereas in the digital world, we don't have a concept of real numbers. We have a way of estimation and representation of real world continuous entities in a digital form. So the difference between, so let me explain that with an example. Think of this, like look at this tuning fork. When it vibrates, its prongs basically take on every position between, let's say, these 2 points. So they don't like vanish from here and then they don't exist here and then they come here. So in real world things don't work like that. In real world things don't like the, for example, think of a digital representation of this tuning fork just by using a single bit. So it would be that either the prong is here or the prong is here. So 1 0 1 0 1 0 1 0. So in between there is no prong. So there is no description of the prong in between these two locations. So it's like it's here and then it vanishes and it's here, then it vanishes, then it's here. It's just in two positions. There is no position in between these two ends. This is how the digital world works. We can make this more precise and we can say we represent these positions not by using just a single bit and 2 levels. We represent them using 4 levels. Okay, so it can be here, 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 here. So I'm just representing a single prong here. So by the way, this is not limited to a tuning fork or a prong. It's about everything. When I move my hand, I move it smoothly between these positions. And my hand exists everywhere. It's not moving from levels to levels. So it's not going from here, 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 here. And there is no hand in between like that times. It doesn't work like that. Time doesn't work like that. For us, time, it's not like we jump from 1 second to the next second, but between those 2 seconds, we don't exist. It's not like that. We exist on the whole timeline. We exist on the whole real number timeline. So if you look at these prongs and now observe your real world tuning fork, you will feel that the position of the prongs, therefore the position of the molecules that are being disturbed by the prongs, are defined on every location, every position in between their endpoints. So for example, you see a real sound being generated here using this diaphragm. So this diaphragm is taking on every position, and these vibrations are being produced on a real number timeline. What's the difference between a real number timeline? So now you can, if we just look at this graph, for a real signal, a continuous time, continuous valued signal, what the real world actually produces, between any 2 points on this number line, there are infinite number of points. So this is a real number line. Therefore, just place 2 dots which are not at the same location, and between those 2 dots there would be infinite points. And similarly, take 2 values on this curve, which is actually the amplitude representation of, let's say, this sound, and there would be infinite values, infinite set of values between these 2 points. This is how the real world works. This is the real world. Now the problem is that in the digital world this no longer works. In the digital world, you need to basically discretize this information. You need to make it discrete. So now what you're going to be learning from here onwards are some of the techniques of discretizing real world entities into your digital world, and also some of the challenges that come along with this discretization. So if you look at this audio signal, it is continuous time. When I say continuous time, I mean defined on a real number timeline, and it's continuous valued, meaning in this case the amplitude is taking on all possible values between any 2 points, right, or between any two time locations. So between here and here, it's taking on taking on an infinite number of values, right? This is how continuous things work. All right. So when you want to convert this into digital form, what does it even mean? What would it mean to convert such a signal into digital form? What it would mean is that we want to convert the continuous time axis into a discrete time axis, which is what we call sampling. So you just read the values of this signal at certain certain time points. You don't have a way of storing all of it. You don't have a way of storing a file of infinite length. What you can do is you can define an array, and you can say, okay, for every second I will take on, let's say, 2 readings. So that would just mean if I just take 2 readings every second, and here is 1 second, so I'll be, let's say I take 1 reading here, and I take, I don't know, another reading here, just assuming. So okay, so this is what you're going to see, and this is what you're going to see. These are the 2 values of the signal that you're going to see. This is the 2 places, these are the 2 places where you have sampled the signal. So you sample the real world. So if you want to really visualize this, और मैं चाह रहा हूँ कि वाकई आपके जहन में ये visualization हो. Sampling the real world means, now look at me, I want to sample the real world. This is how you sample the real world. When my eyes are closed, I don't know what's happening in the real world. When my eyes are open, I take a snapshot and I close my eyes, and I'm no longer reading. I open my eyes, I read the value. So if I'm reading the position of this pen, if I'm sampling the movement of this pen, my eyes are open, so I take a snapshot. The pen was here. And then I open my eyes, the pen was here. Then I open my eyes, the pen was here. Then I open my eyes, but the pen was here. So this is how you do, this is how you convert continuous time into discrete time. That's the first thing. The second thing is, now I cannot represent all of these infinite values of the signal. So I need to somehow come up with a discretization in the value. So I need a discrete time, discrete valued signal. By discrete valued, I mean that how, for example, which is directly related to how I want to store this information. If I want to store this information in a single bit, so I could define it like, if the amplitude is above 0, if it is above equilibrium, I'll call it 1. If it is below equilibrium, I'll call it 0. So that means that all of these values, wherever I sample it, everything below equilibrium would be converted to 0, and everything above 1 would be converted to, above 0 would be converted to 1. So that means that this signal, once I represent it, would look somewhat like this. This is the signal. So whenever, so let's assume I'm doing sampling at a very high sampling rate. So I'm sampling here, 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 here. So I'm getting these points where so wherever the actual amplitude is above equilibrium, I'm getting a 1, and wherever it's below equilibrium, I'm getting a 0. So let's assume this is 0 and this is 1. So this line is just to represent the old equilibrium position. All right, so this is how you convert from continuous value to discrete value. Let's assume I say, no, I want it to be more precise, so use a different way of representing it. So I say, okay, instead of 2, represent 4 levels. So you need 2 bits for that. So 4 levels would mean that maybe I sample here, and I sample here. Let's say I sample here, and I sample here. So I'm just going to get 4 levels. So the signal might be here, the signal might be here, the signal might be here, and the signal might be here. So I'm getting somewhat of a signal like this. And if I just want to make it smooth, it would look like this. But the values, the actual values, would be just present in 4 locations. So this is just saying कि आप अपने signal को कितने levels में represent करना चाह रहे हैं, and we'll be getting into more details of this. So this is just a high level overview of what we're going to do, but essentially converting a signal from its continuous time, continuous valued representation, which is the real world, which is what you're getting from your microphone. You take that signal and then you convert that signal into a digital form. This whole thing is known as analog to digital conversion. This is known as analog to digital conversion. So A to D conversion, or analog to digital conversion, is essentially taking a real world signal, which is continuous time, continuous valued, and converting it into a discrete time, discrete valued signal, which is essentially now a digital signal. All right, so let's begin with a real example. Here you see a signal which is essentially a 2 Hertz sine wave. It's a pure signal, so it's analog, it's real. So f of t is equal to 2 sine 2 pi 2t. So 2 is the amplitude. So you can see that it's going between 2 and -2, and because if you remember, this is 2 pi ft, so the f here is 2, so you can clearly see by 1 second you have 2 cycles, so 2 cycles per second. So you can see that you have a signal here which is a sine wave with frequency 2 and amplitude, peak amplitude of also 2 from the equilibrium position. All right, now how do I convert this into digital form? So again, applying both representations, the first thing would be that we would sample the signal. So that means that we need to define a sampling rate. We need to come up with how many samples we want to take per second. So let's assume we have some sampling rate. So here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You have 13 samples per second. Sorry, no, it continues. The second basically completes here. So it's going to be 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So by the way, there is the mapping between these two is not one-on-one, but let's assume it basically, if it completes here, so these are the number of samples that I've taken over this 1 second. You get the idea, right? So you define a sampling rate, you define how many samples you want to take per second, and this gives you a sampled signal. Still, that signal is continuous valued, but now it's no longer continuous time. Now it's not defined, the signal is not defined between the intervals here. By the way, these lines, when we represent the signal, you're saying that instead of just putting these dots, we are using these lines. So we often do this in signal processing because this helps us visualize that the point is here. If I just put points, it's sometimes difficult to see the points. So you will often see this representation where you have a line and a dot. So this is just a matter of representation. In reality, it's just these dots which represent the values. All right. So this is how the sample signal actually looks like. This is what the sample signal actually looks like. It's essentially now an array where the time axis now is converted into a sample number. It's no longer time, it's just a sample number. So sample number 0, 1, 2, 3, 4, 5, and sample number along with the sampling rate, how many samples did you take per second, can give you the actual frequency and everything, all of that. But you just have a sample number, which is a natural number. In fact, this is in this particular case, it's set of positive integers. So you have 0, 1, 2, 3, 4, 5. So we defined it from 0. You could have easily defined it from 1. So now we're in traditional computer science domain. So you know the differences between starting from 0 and starting from 1. That's just purely your convention that you want to follow. But these are just discrete sample numbers. There is nothing between sample number 0 and sample number 1. You did not take any reading from the input. By the way, where are these readings coming from? These readings could be coming from, let's say, a microphone. So you have a microphone, which is essentially a diaphragm, a surface, which is attached to, I'm giving you one example. So when this diaphragm will move, it's a mechanical movement. You need to come up with a way of converting this mechanical movement into electrical form. So one way of doing that is simply by using an inductance coil. So we know that when we place a magnet between an inductance coil, if we move the magnet or if we move the coil, so if there is a relative movement between the magnet and the coil, there would be induction of current in the coil. So current would be induced in the coil, and there will be a flow of electrons that we can then measure. So this is essentially, so once it moves between its whatever cardinal positions, the diaphragm moves back and forth, we get this signal as a result. So at the maximum positions, we're getting this of the diaphragm, and at the equilibrium position, we are getting these readings, right? So you're getting a real valued, a continuous time signal from it, which you are now sampling. So this is a sample signal. So what you see here essentially is the value of this signal at the sample number n. So, and you can see these are real values now. Obviously, we have represented them after truncation. So there is already, if you think about it, writing them like this is already, it has given you your quantization. It has already given you your discretization in value. But in theory, I'm dividing the two into two separate parts. So yeah, we have not as yet applied any explicit discretization on the value. So this could be a very long value, so 5 4 3 2 1, whatever, infinite recurrence here could happen. All right, so this is sampling, the first step, discretization in time. Two things that you need to remember from this point on is the sample number, which is just because, so now we are thinking of this in terms of storage. So sample number would just be the index of the array where you're storing this, or the I don't know, the line number in the file where you're storing this, and so that's the sample number that you took from the input. The sampling period, which is essentially the interval between two successive samples, so we're going to call it TS, the sampling period, or the sampling interval. So TS seconds, so for example 0.01 seconds, so that means you're taking 100 samples per second, so every sample is taken after every hundredth of a second, right? So that's your sampling period. And the third thing, which is deeply related with it, is the sampling frequency, or the sampling rate, which is 1 over TS samples per second. So this is no longer hertz, this is the number of samples per second. All right, so hopefully this is not very difficult, and hopefully this is fairly clear enough. All right, so as we said, there are two parts, two levels of discretization for the digital form. One, how much of the amplitude for each sample. So we want to convert these values into digital form. So we're going to define, for example, the number of bits that we're going to use for this, and then divide this whole thing into levels. So everything would then basically just match the levels. So for example, if you want to represent the signal in using 8 levels, that means you're using a 3-bit representation. 2 raised to power 3 is 8. So a 3-bit representation would give you 8 levels, a 4-bit representation would give you 16 levels, 5-bit representation would give you 32 levels, a 10-bit representation would give you 1024 levels, a 20-bit representation would give you how many levels? Can someone tell me? So if 10-bit representation gives you 1000 levels, then roughly how many levels does 20-bit representation give you? You should probably pause the video and think about it. All right, so 20 bits would take you roughly to 1,000,000 levels, right? And 30 bits would roughly take you to 1,000,000,000 levels, and so on and so forth. For those of you who have taken my class on computing fundamentals, probably already have this at their fingertips. Others who have taken other classes obviously should also know all of this in as much detail. So as computer scientists, this should not be a problem for you. All right, so that's why I think quantization would be the easier part for you. And then how frequently should a sample be taken is what's known as sampling. So this is the discretization in time. So you see in this diagram, you just see sampling. You don't see you don't see quantization, because you see that not all values are aligning to these straight lines. So once we define these levels, then everything must be truncated down, or everything must be rounded up. So that again is another quantization decision, that how do you take a real value and you convert it into a digital form. Like for example, when you take a float and you convert it into an int, there are mechanisms that you need to learn of how do you do the conversion. So you could be rounding to the lower value, you could be rounding to the upper value, you could be rounding to infinity, you could be rounding to negative infinity, you could be rounding to 0, and so on and so forth. So those are all of the things are standard. So you've already taken those courses and you already know how those things are done. So I won't go into a lot of details of quantization. It's fairly straightforward. You have a real value, let's say between -5 and +5, and you want to convert it into, let's say, 8 levels. So -5 would get, for example, 0. So okay, let me actually write it for you so that we begin and finish it here. All right, so let's say -5 is 0 0 0, and +5 is, let's say, 1 1 1. So everything in between would be equally would take on equal intervals. So you would have a 0 0 1 here and a 0 1 0 here, and so on and so forth. So you have these 8 levels spanning between these two peak amplitude levels, right? And then you will just take every value that you have. For example, you have plus 4.3, and you would just convert it to the nearest level, so either truncate it down or round it up, whatever algorithm you're following, and you would just convert it into one of these values. So as a result, your file would just read either 0 or 1 or 2 or 3 or up to 8 decimal, so sorry, 7 decimal. So these are all the possible values that that you have after your quantization. All right, so let's look at the whole process of analog to digital conversion. Now I hope you have enough concept about it to completely understand it. So you have your analog input, which is again continuous time, continuous value. So this is the signal that's coming in. So you sample and hold. By that, what we mean is in a real analog to digital converter, you have to basically take a snapshot of the exact value of the signal at the instant of sampling. So you sampled it here, you need this exact value, whatever this exact value is. This is a real valued number. So we can store it in, let's say, the potential in a capacitor, and then afterwards convert it. So but we need a snapshot, we need to temporarily hold it. So this is known as sample and hold. All right, so the sampling takes place here, the value of the input signal is read at discrete time values, and next you have this sampled signal. So at each instance of the sample you have a real value. So think of this as an array of real values. In reality, we don't do it like this. In reality, we keep converting. In reality, let's say the first sample, it gets converted, and that it then eventually goes through the analog to digital conversion and we get a digital value. But here, just to understand the process, we have sampled the signal, and now the next step would be to basically quantize the signal. So you take the value of the input and you approximate it to the nearest discrete value, and as a result you get a signal like this. So now this is a sampled quantized signal. This is what you store. This is what is stored in your WAV file. So essentially your signal now is an array of discrete values, and that's what we use for all of our processing. All right, hopefully this is not too difficult to understand. All right, so now the big question is about the sampling frequency. So if we have a higher sampling frequency or sampling rate, the representation of the frequencies would be more accurate. Now what do we mean by that? And this is something that we really need to understand. So as I said, that when we do this analog to digital conversion, there are repercussions, there are side effects, and the first and the most important side effect is related to the relationship between the sampling frequency and the frequency of the incoming signal. So and we really need to understand this, because this can cause major problems in our systems if we do this incorrectly. All right, so obviously if the sampling rate is very high, like we're taking, I don't know, 1 billion samples every second, then you're already kind of close to the real number line. I don't know, I don't mean in the mathematical sense, but you are taking too many samples per second, so you're good. You don't have many problems with at least the audible human frequency ranges. Obviously that's not going to, and even the music ranges, no problems at all. But if the sampling rate is low, if you're taking, like, I don't know, 3 samples per second, then obviously we can intuitively feel that the sound quality would not be good. But what does that even mean? So we have basically a theorem which is known as the Nyquist theorem, so based on the name of the person who came up with this, or this is also known as the sampling theorem. So the sampling theorem simply says that the sampling frequency, and now I need your complete attention, the sampling frequency should be at least twice the highest frequency component contained in a signal. So we know that up until now we are looking at these very simple signals, a pure sine wave, but if you remember from the previous lectures, these things don't really exist a lot in the real world. In the real world, we have complex signals made up of many frequencies. So the Nyquist theorem, or the sampling theorem, says that the sampling frequency, which we're going to call Fs, should be at least twice the highest frequency contained in the signal. In a complex signal, the highest frequency, so our sampling frequency should be twice that. Now this is, although it seems like, I don't know, arbitrary at this point, but we're going to see this is very intuitively obvious as well. Another way of writing this is that if the sampling frequency is Fs, then the highest frequency that can be encoded digitally is Fs over 2. So your Fs, your sampling frequency, should be greater than or equal to twice the highest frequency component of the signal. Now what does that mean? So look at this signal that you have here. uh, it is composed of a single sine wave at a frequency of 1 hertz, right? You can verify that it is one cycle peak to peak per second. Got it with me? So if our sampling rate is for this wave, if we sample this waveform at 2 samples per second, so that would mean that we're going to get, for example, a sample here and a sample here, and then for the next second we have a sample here and a sample here. So that means that we're getting all the highs and all the lows. So at least this frequency can be accurately represented. Obviously, we are missing everything in between, so the signal would probably look like this if we just plot this. However, the frequency of this new triangular wave is exactly the same as the frequency of the original signal. So right now, just bear in mind we're talking about the preservation of frequencies, not the preservation of the quality of the signal. Right now we're just talking about the preservation of the frequencies. Would the frequency be preserved or not? All right. So the reason for this relationship of the sampling frequency being the twice of the highest frequency component is, if you want to save preserve this frequency, you need to take at least one sample when the signal was above the equilibrium position and one sample when the signal was below the equilibrium position. If you are not taking at least two, if you're just taking one, then you don't know if it ever went below the equilibrium position. And let's see that happening. So if we sample at a higher frequency than 2 samples per second, then there are more than enough samples to capture the variation of the signal. So here you can see we have a sample here, and we have a sample here, and we have a sample here. For the first second and for the second second, you have a sample here and a sample here and a sample here. So the frequency would be preserved. So the wave would look somewhat like this. So it's a different wave shape, which is going to give it a different characteristic of quality, but the frequency would remain the same. And by now, after going through the whole semester, you know frequencies are very, very important. So this won't sound exactly like, and we will basically play with Pratt in a minute, not in a minute, in a few minutes, to see how these things sound like, but at least the frequencies are getting preserved. However, if we sample at a frequency lower than 2 samples per second, for example at 1.5 samples per second, then now we do not have enough samples to capture all the peaks and troughs. So see, we have a sample here and we have a sample here. So the first cycle was preserved. We don't have a sample here. We don't have a sample here, but we have a sample here. And we have a sample here and we have a sample here. So essentially what you're gonna get is this, this, and this. If you look at this, this was 1 second. So this was the 1 second mark, and we did not complete a cycle. We completed a cycle at the 2 second mark. At the 2 second mark. So this is our first cycle, peak to peak. So that means that the frequency that we think that this wave has based on this representation, because remember, we don't have access to this signal anymore. We sampled it and we quantized it and we saved it. We just have access to this now. So based on this, there is a new frequency. We did not capture this whole cycle. So this is no longer 2 hertz. This signal is no longer 1 hertz, and its frequency essentially now changed. It's not 1 cycle per second. It's actually 1 cycles per 2 second, at least from what it seems from here. But we'll get into more details of that. All right. So here we are not only losing information, we are running into a phenomena which is known as aliasing. We're getting wrong information about the signal. We are not getting the correct frequency information of the signal. So this is essentially what's happening, that we took fewer samples than were required to preserve all the frequencies, and when we combine them, we get a new wave with a different frequency. So instead of finding the wave to be 1 hertz, we feel that the wave is basically 0.5 hertz. So it is 1 cycle for every 2 seconds. It is 1.5 hertz. 0.5 hertz. So the frequency of the waveform changed. So therefore, the minimum amount of samples that we need in order to preserve a particular frequency in the input signal, is that for that frequency we should be at least capturing 2 samples for each of its period, each of the time period of that frequency. So the sampling frequency should be greater than or equal to twice the highest frequency present in our complex signal. So this is also true for complex signals. So here you have a signal composed of waves of 1 hertz, 2 hertz, and 3 hertz. So therefore, if we want to correctly sample it, we need to sample at least 6 samples per second. And if we do that, it's going to preserve 1 hertz, 2 hertz, and 3 hertz, all components. If we sample at a lower frequency, lower sampling frequency, let's say if we sample at 4 samples per second, what's going to happen? This will be preserved, but this will go away. Now, this should also be giving you ideas. You should be thinking, okay, so this sounds like a nice way of basically removing the 3 hertz component. And yeah, sure, you can. You can use such techniques to basically remove particular frequencies. In fact, this is like acting like what we call a low pass filter. So lower frequencies are passing, but higher frequencies are getting attenuated. But we'll be getting into some of that later in the course. All right, here are some other examples. So you have this analog frequency which is just 0, that is DC. So you like for this, even a single sample would have been fine throughout. So this is like there is no variation. Here in the second case, you have the analog frequency is 0.09 of the sampling rate, which means that the sampling frequency or the sampling rate is 11 times the highest frequency component. So you're perfectly fine. The wave would be correctly represented. If you look at this here, the sampling frequency is 3.2 times the highest frequency component. So if you just combine these dots, you're going to get a wave of the same frequency as the original wave. However, here you have the sampling rate to be equal to 1.05 of the highest frequency component, and therefore you see that now combining the dots basically gives you a new waveform of a different frequency. So this is what we call aliasing. So aliasing is when you start finding new frequencies in your representation of the waveform, the frequencies which were not necessarily present in the original waveform, and this is all because of that you failed to follow the Nyquist recommendation, the Nyquist theorem, the sampling theorem, and you did not sample at the correct sampling rate for the frequencies present in your input signal. Now, this is basically highly related to many of the phenomena that we are quite used to. So one of that is the wagon wheel effect. So if you have seen movies, in movies, जब कभी कोई पहिया चलता हुआ नजर आ रहा होता है, तो कभी-कभी there are times when you feel कि वो पहिया बिल्कुल stationary हो गया, या there are times when you feel कि वो पहिया घूमते 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 एक ऐसी स्पीड पे पहुंचा कि वो उल्टा घूमता हुआ नजर आने लगा. Why does that happen? And basically things are highly related here. So अब मैं यहाँ चाहूँगा कि थोड़ा सा अब हम अपने जहन को खोलें और खाली A to D कन्वर्जन से आगे बढ़ें और ये सोचें कि किस तरह से ये वैगन व्हील इफेक्ट इम्प्लीमेंट हो सकता है. And let's talk a little bit about that. So one of the common impacts of aliasing that we see in our common lives is the wagon wheel effect. So the wagon wheel effect essentially is कि आपके पास एक movie के अंदर, so a movie is basically a stitched together photographs. So आप किसी भी real world occurrence को sample कर रहे होते हैं. So essentially all movies are basically sampling, based on sampling the real world. जितनी भी आपकी digital movie making है, सब इसी के ऊपर based है. So you take a bunch of photographs, for example 24 photographs per second or 30 photographs per second or 28 photographs per second, depending on कि कौन सा आप इसमें जो है method follow कर रहे हैं. Let's say you're taking 30 photographs per second. Now the Nyquist theorem says that at this point कोई भी periodic motion जो उस वीडियो के अंदर हो रहा है which has a frequency, let's say dark light shift हो रहा है, कोई wagon wheel move कर रहा है, गाड़ी का पहिया घूम रहा है, if it has a frequency greater than 15 times per second, then 30 samples per second जो आप उसकी तस्वीरें खींच रहे हैं उसमें वो चीज़ कैप्चर नहीं हो सकेगी, and you're gonna start seeing aliasing. So for example एक पहिया है इस किस्म का जो मैं यहाँ पर एक निशान लगा देता हूँ और ये घूम रहा है. अगर तो ये पहिया जो है वो घूम रहा है ऐसी फ्रीक्वेंसीज के ऊपर जो कि हमारी सैम्पलिंग फ्रीक्वेंसी जिसको कैप्चर कर सकती है, तो वी गोना सी इट टर्निंग करेक्टली. अगर हमारी सैम्पलिंग फ्रीक्वेंसी लकीली या अनलकीली एग्जैक्टली मैच कर गई इस पहिए की वापस इस पोजीशन में आने पे, लेट से ये वापस घूम के रेड स्पॉट जब यहाँ पहुंचा, आपने तस्वीर खींची, फिर यहाँ पहुंचा तस्वीर खींची, तो ये पहिया आपको रुका हुआ नजर आएगा। अब इतना एक्यूरेटली होना यूजुअली बहुत लकी या अनलकी होके होता है। बिल्कुल वैसे ही है जैसे आप किसी एक वेव को सैंपल कर रहे थे और आप सही से नाइक्विस्ट फॉलो कर रहे थे, लेकिन एक सैंपल यहाँ लिया, अगला यहाँ लिया, अगला यहाँ लिया, अगला यहाँ लिया, सो यू आर टेकिंग 2 सैंपल्स पर सेकेंड फॉर दिस, फॉर एग्जांपल दिस इज 1 हर्ट्ज, तो आप 2 सैंपल्स पर सेकंड ले रहे हैं, लेकिन आपको जो सिग्नल मिल रहा है वो बेसिकली ये डीसी मिल रहा है। तो ये दिस इज अ वेरी लो प्रोबेबिलिटी अक्ररेंस, ऐसा होता नहीं है, और क्योंकि जाहिर है रियल वर्ल्ड में ऐसे सिग्नल्स होते भी नहीं है, तो लिहाजा ये चीज़ की ज़रा चांसेस कम है। लेकिन खैर अगर ये आप मैच कर लें तो बिल्कुल एग्जैक्टली यही होगा कि पहिया सीधा खड़ा हुआ नजर आएगा। लेकिन अगर लेट से कुछ ऐसा हो जाता है कि ये पहिया पूरा घूम के यहाँ पहुंच गया, इस जगह पहुंच गया, और आपने अगली तस्वीर खींची, तो अब आपका ब्रेन आपको मोशन बजाय ये मोशन दिखाने के ये मोशन दिखाना शुरू कर देगा, क्योंकि एक स्पोक यहाँ भी पहुंच चुका है ना इसका। तो बजाय इसके कि ये कहे कि ये यूं मूव कर रहा है, आपका ब्रेन इसको इंटरप्रेट ऐसे करेगा जैसे ये स्लोली यूं मूव कर रहा है, रादर देन मूविंग रैपिडली इन a clockwise direction. You're gonna see it moving slowly in a counter-clockwise direction. ठीक है, ये बात समझ में आ रही है? तो इस चीज़ को आगे अगली कुछ वीडियोस में एक्सप्लेन भी करेंगे। I'll basically play 3 videos for you here. The principles are also based on जो जिस तरह वो डेमोन्स्ट्रेट किए हुए हैं यूजिंग उन्होंने स्ट्रोब लाइट से किए हुए हैं। स्ट्रोब लाइट के साथ बहुत इंटरेस्टिंग एक्सपेरिमेंट्स किए जा सकते हैं, बट केयरफुली लिसन टू अ वार्निंग। स्ट्रोब लाइट फ्लैशिंग लाइट होती है, विच इज़ कंटिन्यूसली फ्लैशिंग। कुछ लोगों को इससे सीजर्स इंड्यूस हो सकते हैं। अगर ऐसी कोई केस है तो यूजुअली यू ऑलरेडी नो अबाउट इट। अगर आपके साथ कभी इस तरह की कोई एपिलेप्टिक फिट्स या इस तरह का कोई मामला कभी रहा है, तो फ्लैशिंग लाइट कैन बेसिकली ट्रिगर दोज इवेंट्स। तो इस वजह से इफ़ यू आर प्रोन टू सीजर्स और इफ़ यू आर प्रोन टू सच फिट्स, प्लीज़ मेक श्योर कि आप वो हिस्सा ना देखें। सो जस्ट स्किप दैट पार्ट ऑफ द वीडियो एंड मूव ऑन। और मुझे बता दीजिएगा कि आपने इस चीज़ को समझना है उसके बावजूद भी, और मैं आपके साथ अलग से, मैं या मेरी टीएस आपको और डिटेल में समझा देंगे। ऑल्दो कि इसको ये सिर्फ मैं इसलिए पढ़ा रहा हूँ आपको ये वाला हिस्सा कि आपको रियल वर्ल्ड एप्लीकेशंस ऑफ दिस एलियासिंग एंड द नाइक्विस्ट थ्योरम ये कुछ समझ में आ जाए। दिस इज जस्ट लाइक सम एप्लीकेशंस, देयर आर सो मेनी अदर्स, बट ये वो ऑब्जर्वेशंस हैं जो हम यूजुअली कर सकते हैं। इसमें वो आपको वो भी दिखाएंगे कि आप अपने फ़ोन पर स्ट्रोब लाइट इंस्टॉल कर सकते हैं। यू कैन बेसिकली सी योर फैन स्टैंडिंग स्टिल एंड सो ऑन एंड सो फोर्थ। ये इफेक्ट जो पुरानी ट्यूबलाइट्स के साथ आपने होते हुए भी देखा होगा कि कभी ट्यूबलाइट जब खराब हो जाती है, फ्लैश करने लगती है, तो देयर आर टाइम्स व्हेन वी कैन सी सम ऑफ द विंग्स ऑफ अ सीलिंग फैन स्टैंडिंग स्टिल। So that's the strobe effect. तो अगली चंद वीडियोस देखिए, those are interesting things which are being shown in those videos, but with the clear warning, अगर आपको flashing lights तंग करती हैं तो please don't watch the videos, and then move on to the next slide of my lecture.
This video does contain a strobe light, so if you are prone to seizures, please do not watch this video. Now, if you've ever watched a video or a TV show that has a car in it and the wheels appear to be spinning backwards, you are witnessing the wagon wheel effect. We're going to explore what's happening through this demo. Here we have a fan that is coated in glow-in-the-dark paint, and the fan's motion is never changing, but it does appear to be. The only thing that is changing is the speed of the strobe light. We can change how fast or slow the strobe light flashes. And if you listen, you can hear like a ticking or a rattling. That is the sound of the light flashing on and off very quickly, and you can hear that rate change throughout the video. So a movie is just basically a bunch of pictures that are taken really fast, kind of like a flip book. And each of those pictures we refer to as a frame. So each frame of a movie is a picture. Now, different things record at different frame rates. Your phone typically records at 30 frames per second, which means that every second it takes 30 pictures when you're recording a video. In the demo, when the strobe light flashes, we can see the fan for a quick moment. But when the light turns off, it still spins, we just can't see it. Every time the light flashes, we are seeing a frame of the fan. And you'll notice that the fan, while spinning clockwise, appears to move counterclockwise in the frames, and that's the part that we see. So while the fan is spinning clockwise, we interpret it as spinning counterclockwise because of the frames that we are able to see. This is what causes the wagon wheel effect. So we're going to watch it again, and I want you to listen to the sound of the strobing light to notice the changes in the frequency, and also notice that it looks like the fan stops at one point. What's happening here is that the flashes are happening at the same time that the blades have a chance to get into the same position as the previous frame. So essentially we're not seeing any kind of motion because it looks like they're just staying in place. Now you can do this at home too. You'll need a fan, a smartphone, a strobe light app for your phone, and a dark room. The blades were painted with a glow-in-the-dark paint, which makes this effect much better, but it can be done pretty decently without the paint. Ask your teacher for more information, and most of all, please be careful. Thanks for watching.
Here we see droplets that appear to be falling in slow motion. This effect is due to the strobe light flashing at almost the same rate as the pump producing the drops, about 60 flashes per second. While this looks pretty, you might be wondering how a flashing light can make droplets move in slow motion. Let's start by looking at a computer animation showing drops falling with a strobe flashing at the same rate as the drops. The animation really is slowed down, so we can study the details of the droplet motion. The dark green dots show the true motion of the drops as they fall. About once a second, there is a bright flash of strobe light that illuminates the drops. Even though the strobe flash is very brief, your eye continues to see an image of the drop fixed in space at the moment the strobe light flashed. This effect is known as persistence of vision and is shown in the animation as the bright green dots. The drops appear to be motionless because each time the strobe flashes, a new droplet appears at the same location as the old droplet. Since all the droplets look alike, we see what looks like a series of droplets hanging motionless in space. If we slow down the rate of strobe flashes by a slight amount, the effect is to make the droplets fall downward in slow motion. What really happens is the new drop reaches the position of the old drop, and then falls a little bit past the position of the old drop before the strobe light flashes again. Thanks to persistence of vision, we see the drop fall only a tiny distance downward from one flash to the next. That's because we can only see the drops when the strobe light is flashing, and we don't see any of the motion that takes place when the strobe light's off. We can make the droplets appear to fall upwards by flashing the strobe light slightly faster than the drops. In this case, the strobe light flashes just before the new drop can fall to the previous position of the old drop. Instead of seeing the old drop fall down, persistence of vision leads your eye to connect the image of the old drop to the image of the new drop that is slightly higher than the old drop. The net effect is the drops now appear to fall upward. Persistence of vision doesn't really work unless the strobe flash has happened often more than about 15 flashes per second. Here we see 60 drops per second with a slightly faster flash rate, making it seem like the drops fall upward. You can make your own strobe light to reproduce this effect on your own. Thanks for watching.
Alright, so now you have seen aliasing in action in our daily lives. इससे आगे मैं चाहूँगा कि आप अपने तौर पर खुद से देखें, खुद से पढ़ें. We have all seen it. We have all seen flickering computer screens on a in a movie. So movies के अंदर जब भी computer screens नजर आती हैं, at least in the old movies, you always see that flicker. So that's also a very related concept. So you should be reading up on those things on your own. Aliasing applies in the image processing world quite a lot, as it does in the audio processing world as well. We'll take one example from the audio world as well in a few minutes. So ye janab, in one screen you can see the whole analog to digital conversion process. So you take the original signal, which is a continuous continuous time, continuous valued signal, you sample it at a particular sample rate, and you have now seen the constraints that we have for the sampling rates and the relationship with the highest frequency components in the signal, and then finally you quantize that signal. So for example, you say it's a 64, it's a 16-bit signal, so that means it has 64K levels for quantizing the signal. Now we have these are just based on some applications that of these speed signals. So human ear can hear up to 20 kilohertz. So that means that the highest sampling frequency that we need to encode just the human hearing range would be 40 kilosamples per second. And similarly, for speech, usually what we do is, like for telephone quality speech, we just encode up to 4 kilohertz of frequencies. So you have already seen that all the important formats are already covered in that range. So this is the telephone quality speech, in which only up to 4 kilohertz of frequencies are reproducible, which means that we sample at 8 kilosamples per second. Now let's go to Pratt and let's play with these concepts a little bit, and then we'll come back and continue. Alright, so what I'm going to do is I'll just take a sound, example sound from the press corpus, the phonetically rich Urdu speech corpus. So I'll just take one example file from it, and again the warning, it would be strange sounding as the press corpus is, as I already explained. So let me just open and view this file. So here is the file that we have. This is file number 32 in the listing. Let me play this. खानकाहों में ज़बूं हाल नशई गुलेल चोरी करने के लिए छड़ियाँ उठाए खड़े हैं. Okay, so खानकाहों में ज़बूं हाल नशई गुलेल चोरी करने के लिए छड़ियाँ उठाए खड़े. Okay, so if you remember, we basically reverse engineered these sentences from the words which were phonetically rich. So this was done by our linguists, and these are the sentences that they came up with. All right, so you can see that in this file we are easily looking up to like 5,000 hertz of the file, and the spectrograms go all the way up to 5,000 hertz. All right, so now what I'm going to do is I'll just take this file and I'll try to modify this, I'll convert this, and I'll resample it. So we can see that right now it is sampled at 10,000 samples per second, or so by the way, I'm continuously using the term samples per second for sampling frequency. You will also see hertz here. So by hertz here, it would mean the same, like number of samples per second. So just never be confused by that. So all right. So let me just bring it down to say, all right. So let me make it 6,000, or in fact 8,000. So what would 8,000 samples per second imply? That the highest frequency component in our audio can now be only up to 4,000 hertz, right? So let me do this, and we have this file. Let me also do another one, and then we'll look at them together. So convert, resample, and let me make this 6,000, apply, and let me go to the original and create another one at 4,000, apply. Let me create another one at 2,000, apply, and another one at 1,000, apply. All right, so now I don't need the last one. Now I have these different files. Let's open this first one. And very interestingly, we see a sharp line at exactly 4,000. So I won't be able to position my cursor exactly, that you already know by experience if you have already played with Pratt. But this line is exactly at 4,000 hertz. So there's a sharp cutoff at 4,000 hertz. Let's try to hear this telephone quality audio. And to compare it against the original one, let's play the original. खानकाहों में ज़बूं हाल नशई गुलेल चोरी करने के लिए छड़ियाँ उठाए खड़े हैं. खानकाहों में ज़बूं हाल नशई गुलेल चोरी करने के लिए छड़ियाँ उठाए खड़े हैं. So I'm not sure whether you can hear it or not, because I'm recording it using my microphone, but just do it on your own, and you will feel there's a difference. There is a difference in the like the sound appears a little bit, sounds a little bit muffled in the lower when it's sampled at a lower sampling rate, जबकि जो original file है वो ज़्यादा हमें wide feel होती है, ज़्यादा हमें उसमें space feel होता है. Okay, let's go to the 6,000, and now we should have a cutoff at 3,000. All right, let's see if we do. Yep, we have a cutoff at 3,000. Let's play this. खानकाहों में ज़बूं हाल नशई गुलेल चोरी करने के लिए छड़ियाँ उठाए खड़े हैं. So interestingly, we can still hear it. But now let's go to this 4000, which means a cutoff at 2000. And now some of our formants are basically even f2 is going out of the bounds. And now, if you play it on your own computer, you will feel that some sounds are sounding different. In fact, especially sounds like sh, which have a clear high frequency component which is needed for correctly rendering them. You will start hearing, your brain will start making it sound as if the person has a speech disability. जो बोल रहा है इसके अंदर वो उसकी कोई speech disability है जिसकी वजह से वो अपनी phonemes को नहीं सही pronounce कर सक रहा, but you're still able to make the meaning. By the way, it's also an interesting experiment if you start from the most attenuated file first एंड सी की आपको सुनाई देती है, ये समझ आती है या नहीं. सो दिस रिक्वायर्स टू ऑफ यू. अपने दोस्त के साथ ही एक्सपेरिमेंट करें. एक फाइल ने अननोन, उसको पहले लेट से बहुत लो सैम्पलिंग रेट के ऊपर ले जाएं. दोस्त से कहें अब आप वो आपसे कहे कि इसको सुने और बताएं क्या कहा गया. एंड यू प्रॉब्ली वोंट बी एबल टू टेल. तो आपको याद होगा मैंने आपको जो एक इससे पहले एक्सपेरिमेंट्स करवाए थे जिनमें एक ऐसा भी था जहाँ पर साउंड को नॉइजी करके पहले सुनाया था और आप नहीं समझ सके थे, फिर ठीक करके सुनाया था और आपने सुन लिया, और फिर अब नॉइजी सुनाया तो आपको फिर भी सुनाई देने लगा. तो वो चीज़ यहाँ भी होगी. सो योर परसेप्शन इज प्लेइंग अगेंस्ट योर, इनफैक्ट इन योर फेवर हियर एज वेल. All right, so this is just 1000. So you technically you should not be hearing a lot of this, but still you would be able to make some of it. All right, so you can still hear it because you already know what was said. And then let me play just one more. All right, so as we saw in the last in the quick video, that indeed the Nyquist frequency and the relationship between your sampling frequency and your highest correctly reproducible frequency component in the file, it actually holds, and it holds perfectly. All right, so now that we have understood all of that, we are ready to basically move on with some of the things that you'll be doing as part of your assignment. So I won't be going into any details of this, but now you know that you can represent a file as a speech file or an audio file as an array, which could be written also to a file. So here you have an example of a WAV file format. So this is the Microsoft WAV file format. So you would need to learn this, and you would be basically processing your audio files as WAV. This is the simplest and lossless method of storing your files, and obviously it produces comparatively bigger file sizes, but we'll start with this. Just going over this really quickly, for the WAV file, you have a header which gives you some information about the file that is actually the way the data is actually stored in the file. So for example, you have the number of channels, like whether it's a mono file or a stereo file, the audio format, and so on and so forth. So you'll be reading these things on your own. I won't be going into a lot of detail for this. You'll be given some pointers about this in your assignment statement, and then when you're going to get an assignment about this, and then you will be playing with this on your own. So there is really nothing to teach here. You need to basically just go through the standard, write a way to a driver to basically extract the audio file information, and then basically play with the file and do interesting stuff with it. All right, so now we are ready to start looking at some of the basics of discrete time signals. Now you know what discrete time signals are. So now we can basically start looking at some of these elementary signals that we'll be using a lot in our signal processing journey. So let's quickly look at them. So the first one that we're looking at here is actually a very important one. It's known as a unit impulse signal, or it's also known as the delta function. So the unit impulse function or the delta function. So the delta function is simply defined as that it has a value of 1 at time 0, and it has a value, or n is equal to 0 in this case because we are defining the function over n, and it has a value of 0 everywhere else. So this is known as a unit impulse or the delta function. So remember this one. This is really very important. So we'll be using this quite a lot. By the way, just giving you some idea of the notation as well. Sometimes we're going to write the signals like this. Sometimes we're going to write, for example, this delta function could also be written like this. This is also the delta function, and in this case, to indicate where you have n is equal to 0 or t is equal to 0, we'll just place an arrow here. So when you represent a signal in this array format, to represent the t is equal to 0, or to represent the n is equal to 0, like the midpoint or the origin, we just use an arrow. So this is an alternate notation that you'll be seeing a lot in the upcoming videos, in your quizzes and in your assignments and everywhere. By the way, for all of this, I'm following various books on digital signal processing. So the one I have here with me is Digital Signal Processing by John G. Prokis and Dimitris G. Monolakis. So that's one book. I'm also following the famous signal processing book by BP Lathi. So feel free to look up any resource on this. These books, by the way, I'm not sure about this one, but the other one, the BP Lathi book, is definitely available as PDF for download online. So you can do that, or you can buy the book, or you could just borrow it from the library. But yeah, you can look up these topics in more detail in these books, and that would be a reliable resource. All right, so the next important signal that we're going to look at is a unit step signal. So it's defined as its value for the unit step signal is 1 for n is equal to 0 and beyond, and its value is 0 for all values of n less than 0. The next one is the unit ramp signal. So the unit ramp is defined as 0 for all values of n less than 0, and equal to n for all values of n greater than or equal to 0. So by that definition, this value would also be 0, but yeah, writing it this way is more convenient. So this is your unit ramp. Here we have indicated it as u_r. All right, so this is the exponential signal, and you would need to basically convince yourselves of what I'm showing you here with some actual examples. But a is it could be real valued, it could be a natural number, or it could be a real number. And if so, what the signal that you're looking at here is known as an exponential signal. Now, it could indicate an exponential growth, as here, or an exponential decay, as you see on the left. If the value of a is between 0 and 1, then you're going to see an exponential decay. If the value of a is greater than 1, then you're going to see an exponential growth. If the value of a is equal to 1, then it's going to be just stable, straight line. If the value of a, on the other hand, is less than 0, so we have two examples here. If it is between 0 and -1, then you're going to see this alternating exponential decay. And then because obviously for the even numbered exponents, you're going to see a positive value, and for odd number ones, you're going to see a negative value. And if the value of a is less than -1, then you're going to see this alternating exponential growth like curve. So it's going to grow like this, and it's going to grow like this. All right, so this is also an important signal for you to know and have it in your toolbox. All right, so now let's look at some of the basic operations. So up until now, we have seen all right, so the next operation that we're going to look at is what's known as folding or reflection. So that is essentially a flip around the vertical axis. So you essentially take your original signal and you just flip it around the vertical axis. So this goes here, and 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 so on and so forth. So it's just a flip. So mathematically, all you do is you just replace the independent variable and just the variable, not anything around it, with -n. So this important precaution, you will find it very useful when we're going to look at our next example. So simple flipping or simple folding or reflection is fairly easy to implement. It's just take your signal and flip it around the vertical axis. However, when you're doing multiple operations one after the other, like for example, when you want to do a folding followed by this +2 operation, so the +2, if you remember, is time advancement. However, when it's applied to a folded signal, it actually leads to a time delay. And what happened here? So this is basically the thing that I wanted you to be careful about. And what's going to really help you, so what's happening here is that folding and time shift, these two operations are non-commutative. So when you apply it in one direction and when you apply it in the other direction, the results are not the same. So the way you should be looking at these things, and the easiest way to solve this, is just by using a table. So you need to just make a table. So once you make a table, you have these n's and you have these -n's. So you have folded. So plus 2 becomes minus 2 becomes plus 2, and plus 1 becomes minus 1 becomes plus 1, and 0 remains 0, and 1 becomes minus 1. So this is your folding operation. And next you apply, for example, the same delay operation here. So in reality, this is just a plus 2 operation. So when you apply a plus 2 operation here, which should have actually advanced it, however, once you apply it here, so plus 2 is 4, plus 1 plus 2 is 3, 0 becomes 2, and so on and so forth. Now let me clean this up a little bit and see what happens when we actually map these numbers. So finally now you need to place x of 4 at minus 2 position. All right, so let's do that. X of 4 is this value, right, and it should go to the value of to the place of in your final output. It should be at n is equal to minus 2. All right, that works. Next, x of 3 goes to minus 1, so x of 3 goes to minus 1, perfect. X of 2 goes to 0, okay, so x of 2 goes to 0, still working in our favor. X of 1 goes to 1, so x of 1 goes to 1, so it remains essentially where it was. And x of 0 goes to 2, so x of 0 goes to 2, and everything is perfectly fine. So now you don't need to actually remember which one was advanced and which one was delay, because it gets confusing after some time. But if you just create the table, you're gonna be fine. Let me show you another example with this. All right, so let's look at it. Look at a more thorough example using the table. So you have the original signal here, which is your x of n, which has 0, 0, 0 at sample numbers minus 5, minus 4, minus 3, and then you have a 1 at minus 2, a 2 at minus 1, and a 3 at the origin. And then you have the values 4, 5, 6, 7, minus 2, 0, 0, 0 at the sample numbers 1 to 8. All right, so we have this signal. Now I want to calculate x of n plus 2. So to calculate that, I first calculate the new indices. So I just do an n plus 2. So minus 5 becomes minus 3, minus 4 becomes a minus 2, minus 3 becomes minus 1, and so on. And now all I need to do in order to calculate this is just to figure out, so what do I need to put at x of minus 5 at this location. I'll just bring the value from this position in the original signal. So I'll bring it from minus 3. All right, so this 0 comes here, and then here I need the value from minus 2, which is 1, and here I need the value from minus 1, which is 2, and so on and so forth. So I'm going to fill this whole thing up, and because I don't know the values from the original signal at 9 and 10, so either I can assume that to be 0 and put zeros here, or I can just leave it blank as I've done here. All right, so this is now my shifting towards the left, or time advancement. As you can see that in place of 0 in the original signal, we have the signal from sample number 2. All right, now let's do time delay by doing a negative. So if I do a minus 2, so minus 5 becomes minus 7, and minus 4 becomes minus 6, and minus 3 becomes minus 5, and so on. And now I just bring values from these locations in the original signal. So here what I need here is value from minus 7. I don't have a value from minus 7, so minus 6 and minus 7 are not available. Minus 5 is 0, minus 4 in the original signal is 0, minus 3 in the original signal is 0, minus 2 is 1, and so on. So I get a time delay of the signal. The original signal has been delayed by 2 units. All right, so at 0 I have minus 2, the delay. All right, now I'm doing folding here. So for folding, I just reverse it. So minus 5 becomes 5, and minus 4 becomes 4, and similarly 8 becomes minus 8, and 7 becomes minus 7, and 0 remains 0. This is important. All right, so minus 5 comes here from the original signal. This is the 5, so this is minus 2, and from the 4th position this is 7, and so on and so forth. So I calculate it, but I do not have values for minus 6, minus 7, and minus 8 in the original signal, so therefore these remain blank. Now if I want to do a minus 2, minus 2 and see what I get, I just recalculate the indices. So I do a minus n plus 2. So this 5 becomes minus 5 becomes 5, and then I add, so I do a minus 5 minus 2 to this, and this gives me, so this becomes a minus 5 becomes 5, and then I do a minus 2 to this, and this becomes 3. Now the important thing to note is I do not do a minus 5 and then minus 2, and I do not do this whole thing to be minus, which would become 5 plus 2. I'm not doing this. What I'm doing is I'm doing it step by step. So what I've done is I've taken it from, so let me clean things up a little bit. Give me 1 second. This is important, so I need to really clean up the board for this so that you don't get confused at any step. Because these operations are not commutative, therefore we have to do them step by step. So the first step is I take this minus 5 and I do a folding of it, and it becomes a plus 5, and now I do a minus 2 on this, which becomes 3. So minus 5 becomes 5 and 5 becomes 3, minus 4 becomes 4 and 4 becomes 2, minus 3 becomes 3 and 3 minus 2 becomes 1. This is how I'm getting the new indices. Remember this. This is important. This is important. These are step-by-step operations. All right. Once I'm done with this, now I just bring the values from the original signal. So from the location 3, 6 comes in, from location 2, 5 comes in, and so on. It's straightforward from there onwards. Let's do it from on the other direction. All right, so let's use a different color. So I want to do minus n plus 2. So I do first minus n, which 5 becomes minus 5 becomes 5, and now I do plus 2, which is 5 becomes 7. Minus 4 becomes 4 and 4 becomes 6. Minus 3 becomes 3 and 3 becomes 5. All right, and now I just bring in values from the original signal in these locations. So I don't have a 6 and a 7. I actually do have a 6 and a 7 in the original signal. So this would be 0 and this would be 0. And then I have a 5, and at 5 I have minus 2 here. And at 4 I have 7. So I have 7, and so on and so forth. So I keep populating this until the point of minus 5. I don't have a minus 6, so I leave this blank. So now you can see clearly that the signal moved in this direction for this minus operation, whereas for this minus operation on the original, it moved in this direction. So you see the change of directions, but you don't care about them because your table is perfectly giving you the right values in both cases. All right, so another basic operation on these discrete time signals is the time scaling function. So the time scaling is just you multiply n with a number. So for example, in this case, this omega is just an integer, so you multiply it with omega, and this is known as, if this is not if this is greater than 1, then this would become downsampling. So what does that mean? So again, you can make a table, and the table would give you the perfect values, but essentially what you're doing is that here you have x of n, and here you have x of 2n. So by 2n we mean that 0 remains 0, that's perfectly fine, and 1 becomes, so 2 comes here, and 4 comes here, and 6 comes here, and similarly minus 2 comes here, and minus 6 comes, so this is 2, so minus 4 comes here. Where is minus 4? Minus 1, minus 2, minus 3, minus 4 comes here, and minus 6 comes here, and so on and so forth. So this is time scaling, and essentially this is compression. As long as this mu is greater than 1, you're doing a time scaling or downsampling. So this is essentially like downsampling. You are reducing the sampling rate of the original signal. But if you replace this mu to be between, if you change it to be between 0 and 1, let's say this is, instead of 2, this is 1 over 2, you're essentially upsampling. Now you want to basically create more samples than there were in the original signal. So you would be bringing in samples from this location, this location, this location, this location. So you want essentially here x of n over 2 would mean that for 1 you need a sample from 0.5, n is equal to 0.5. For 2 you need a sample from 1. For 3 you need a sample from 1.5. You don't have these samples here in the original signal. If you do have them, you bring them on. If you don't, then you need to come up with another way of interpolating these values and figuring out what the value here would be at 0.5, at 1.5, at 2.5, and so on and so forth. So there are ways of upsampling signals, oversampling signals, but they would involve estimation of the value, because you don't have those values by definition in the original file, if that was the sampling rate for the original file. I hope this is clear. By the way, your folding operation is also another example of time scaling, where your mu is just -1. All right, so this is your time scaling function. Okay, so you can also do combined operations. You can cascade the operations one after the other, and this is the most general form of this, x of at minus b. So a is your scaling function, and this minus b is basically your time delay or advance functions, or your time shift function. So certain complex operations require these, so these are simultaneous use of more than one operation. So for example, for this one you can time shift x of t by b to obtain x of t minus b, and then now time scale the shifted signal, that is, you replace t with at, so you just do the time scaling on this t, right, and this becomes at minus b. You don't do time scaling on both of these, just on one. All right, the second way of obtaining the same is you time scale x of t by a to obtain at, but now that you have time scaled, now the shifting would basically need to be changed, because now you have basically downsampled the original signal. So now time shift at by b over a, because now the meaning of the sample numbers have changed. So you replace t with t minus b over a to obtain x of a of t minus b over a, and this becomes x of at minus b. So you can do it in both of these ways. Obviously this appears, and this also is easier in practice to implement. In either case, if a is negative, time scaling involves time reversal. So for example, you have a signal which is this. So you have x of 2t minus 6 that you want to obtain. So the first way you do this is you can delay x of t by 6 to obtain t minus 6. This is what we have done earlier in our table example. And for this one, so then you time compress this whole thing. So you replace t, just the t, with 2t to obtain x of 2t minus 6. So this is how we have worked with our tables, and I would recommend this path. It's easier. The other one is that you first time compress by factor of 2. So whatever factor you used here, you have to use on this this shifting as well. So now you delay this signal by 3, because the original delay was 6, so you delay by 6 by 2, and then you get x of 2t minus 6. So these are the combined operations that you can apply on your signals. Finally, and we'll basically stop here, this is the last one, and this is the amplitude scaling, sum or product. So these are all operations on amplitudes. So the amplitude scaling of a signal by a constant a is accomplished by multiplying the value of every signal sample. So all of these are basically sample by sample. So every signal sample by a. So consequently, we obtain a of a multiplied by xn. So minus infinity to infinity. That's the whole length of the signal itself. So you go to each and every location. So in your array, you go to every index and multiply it with a. So that's as simple as it is. The sum of two signals, x1 of n and x2n, is the signal y of n, whose value at any instant is equal to the sum of the values of the two signals at that instant. So you just add the corresponding values. So you have the two signals and you add index 0 into index 0, index 1 into index 1. So the value at index 0 is added to the value at index 0 in the other signal. So you just add them together. So x1 of 0 gets added to x1 of x2 of 0, x1 of 1 gets added to x2 of 1, and so on. The product of two signals is also defined on sample to sample basis. So again, you multiply these two, so you just multiply the corresponding values, 0 with 0, 1 with 1, 2 with 2, and so on and so forth, and you get the product of the two signals. All right, so we have reached the place from where onwards we will be looking at now more complicated and more interesting operations. So we will essentially stop here, and in our next lecture we'll start looking at operations of convolution, correlation, some of the more interesting operations that we can perform on these signals to get interesting outcomes. We will also be looking at another very useful operation, which is windowing, but before that we will basically look at some assumptions about the signals that we are dealing with. Thank you so much. Inshallah, अगले lecture में मिलते हैं.